then. Hi everyone, welcome to this webinar, The Models That Govern Us, How Mathematical Models Shape Our Decisions. My name's Flora, I work in the marketing team here at the London Interdisciplinary School. We're a new East London institution that offers undergraduate and postgraduate programs, as well as professional courses. We teach students how to tackle complex real-world problems by applying knowledge and methods from a range of disciplines across the arts, sciences, and humanities. If you'd like to find out more, please visit lis.ac.uk. Today, I have the pleasure to present Dr. Catalina Pesce, who is leading this webinar. Catalina is an assistant professor here at LIS. She studied engineering and mathematics at the University of Chile and did a PhD in mathematics at the University of Oxford. Her research interest is the analysis of partial differential equations, and she currently teaches a wide range of quant and research methods here at LIS. Alongside Catalina, we have another faculty member, Dr. Anson Chung, and third-year undergraduate student, Dylan, who's here to answer some of your questions on the chat. Questions are highly encouraged throughout, and please do leave them in the Q&A section of the chat, and we'll either answer them directly or at the end. The format of today's webinar is a 40-minute presentation, followed by 20 minutes of questions at the end. So thanks so much for joining. Take it away, Catalina.
Thank you, Flora, for presenting me. Well, today I want to take all of you on a little tour of the land of mathematical models. I will be your guide, so thank you for traveling with LIS today. Before we get into the maths of it all, I want to say thank you to the people that are behind the scenes here. So as Flora said, well, she is presenting today. She's presenting me. And we have Dylan, who is a student that I think likes my models because she has taken a few of them. And so she knows a lot about what I will say today. And of course, Anson, who is an associate professor here at LIS, and he will be answering any math questions that you have in the chat. So yes, thank you all of you who are behind the scenes. And so I've told you a little bit about us, and now I'm going to tell you a little bit about me, but I also want to know a little bit about you. So please feel free to go to menti.com. So it's here in the slides in the bottom where I'm looking at with my red dot. So you can go to menti.com with that code, or you can just use your phone and use the QR code. And I basically want to know, what is your maths level? So are we talking GCSEs? Do you do an A level in mathematics? Do you have some STEM undergraduate or professional course in your belt? So I want to know that about you. And I also want to know if you have ever made a mathematical model. And we'll talk more about that later. While I tell you a bit about me, you can answer the questions. So what to tell you about me? I used to be a very indecisive person when I was 17 years old, and I really wanted to go to uni. However, because I was very indecisive, mainly because I liked every subject, I had a hard time. LIS did not exist in those times. I had a slight inclination towards physics and not mathematics, which is what you would expect, I think, from this talk. But I had a slight inclination towards physics because it allowed me to understand how things worked in the world. And I've always been very keen to learn that. So because I had a slight inclination, I went, well, I don't really want to decide forever on a discipline. So I did 2 years of general engineering. And I started to hear these words, mathematical modeling, and we'll get into that in a second. But I also kind of fell in love with maths, which I think it's a very weird thing to fall in love with, but it's the truth. And then I went on to study the specialty in mathematics in engineering. Then I did an applied maths master's, where I looked at equations that describe liquid crystals. And if you have a smartphone, then you have liquid crystals, because those are the ones that make up screens in smartphones. And then I went to do a PhD at Oxford in mathematics, looking at equations that describe how phase separation works in liquid mixtures. But today I'm going to talk about other types of models. Okay, so now I want to know about you. So I'm going to stop sharing this screen and I'm going to share your answers. So let's start with the first one. Okay, so we have a few answers here. So we have lots of people with GCSE level, lots with A level, a few less with more higher education in maths. That's okay, that's what you would expect, I think. But yeah, so we have a very wide range group, which I think is also reflective of LIS students, which is great. So the next question was, have you ever made a mathematical model? So some yeses, that's really good. And please put in the chat which mathematical models you have used, if you can tell us a little bit about that. And lots of no's, which I think is very indicative of what we think is a mathematical model, because I'm going to go back to my slides now. So let me know if you can see them. That's okay. So going back to my slides. So you have, I'm pretty sure all of you have made a mathematical model in your heads at some point in your life. And this is because models wear many disguises. So as we can see in this picture that I made, with the help of Google Maps, of course, if imagine that it's a Tuesday afternoon, like maybe today, you and two of your friends are meeting for a talk at LIS, but you're all coming from different parts of London. So Hackney, Paddington, Peckham, and so on. And maybe you, when you talked about meeting there, you said, oh, the one that gets there first could get us all coffee. And you want to know who will get there first. That is a mathematical model, because you had to decide on things. You had to take into account what modes of transport people would use. Would everyone use underground? Would you use a bus? Would you use Uber? So that is one decision. The other is, are you trying to get there first or last? So time is of the essence. You might also be interested in knowing the weather and other things around your travel arrangements. And now that you have all of your variables, you put that in your head and you say, oh, okay, you make an educated estimation of, yes, this person will get there first, so I don't have to worry about getting coffee for everyone. So that is a mathematical model. So today we will see a few examples that are a bit more formal than this, but just be sure you have done this before, okay? So let's get into the maths a little bit. Okay. So what is a mathematical model? And a mathematical model is a way for us to abstract the absolute most essential aspects of real life, of a real life problem, into an equation, something that we can solve, something that we can obtain an outcome that we can quantify, that we can predict. Okay, so that is the main idea. That is what a mathematical model is. And they creep up in the weirdest places sometimes. So you can find mathematical models in economics, in politics, of course, in physics. Everything that moves basically and has a law of movement is a mathematical model of something real. In chemistry, if you want to figure out how much of a certain chemical to put to get a certain reaction or amount of outcome, that is a mathematical model. Population growth in biology or population studies, that is also a mathematical model. Epidemiology is filled with mathematical models about the spread of diseases. If you are trying to figure out how to decide on something where you have groups of people and you're trying to decide on something together, that you can quantify somehow, that you can each has their own gain from this, then that is also a mathematical model in politics, for example, or economics, if you're studying how two companies decide on a price. Well, I could go on and on, but I want to make an emphasis on one that is over here at the end, data science. So mathematical models have a lot to do with data because of the real life aspect. So they are connected to data in the way that they use it to make these equations, okay? And there are certain levels of how much we use data depending on the model. But my point here is that data has become really, really important in the last 20 to 30 years, not only because it's more available, but also because we require more of it, and we can use more of it now and analyze it more in depth because we have more tools. So if data is the new oil, then models are the new pipelines. So they are the things that give shape to the data. And they are also the refineries. They help us tell a story. They help us predict things. And this is a quote by Dr. Erica Thompson. She's an expert in modeling for decision-making at UCL. She has a few talks if you want to see her. And we're going to talk about some of what she has done later. But this is why it's so important that we understand mathematical models, because they give shape to the raw data. And without them, we wouldn't understand what's going on. Okay, so let's talk about what types of models we are actually looking at. So we're basically going to separate them into two categories. So the first category is the one in red here. And let me tell you this story. So you are interested in a certain population over the years, okay? And you have some data. So you have these crosses here that are the data. So these blue crosses tell you a little bit about the population over the years. Now, we could just draw a line of best fit, okay? We could just like interpolate, okay? Interpolate means that we are connecting inside the dots, okay? And this type of model where we draw a line or maybe something different, but still that where the data is the main bit that goes between the points, those models we will call data-driven, yes? Because the data emphasizes the type of line or curve that we're gonna fit. Then if we want to go above and beyond, we would be extrapolating. So extrapolating is when we go outside of the data that we already have. So it would be like going outside of the box here, okay? And extrapolation is very difficult because we don't have data there. So that means that we need to make assumptions. We need to decide, okay, what is happening outside of this, okay? And we need to make those assumptions based on justification, based on laws, and that kind of thing. So now I want to tell you a bit about how we actually do this. What is the process? So imagine that we have a real world problem. For example, we're trying to predict the weather tomorrow here in Whitechapel, for example. So that is my real world problem. I'm trying to predict the weather tomorrow in Whitechapel. So I'm first going to simplify. I'm going to simplify the problem, okay? Because I cannot take into account every possible factor, yes? So I'm going to decide on which variables I'm going to use. So I'm interested in pressure, for example. I'm interested in temperature. I'm interested in time, position. I'm interested in humidity. That's a very important one. So you decide on those variables first. And there are so many variables that I'm not taking into account. Like if there is a pond in the park, that's not going to change much the humidity of the whole borough. So I'm not going to take that into account, yes, but I will take into account the average humidity, okay, of today. So then we would translate this into mathematical notation. And what that means is just we give it a new name. So pressure could be P, wind speed, for example, could be S or B or something like that. And then we need to put those together. We need to do what we call derive the model. So we need to put these variables into an equation. So we need to know if we change temperature, what happens with pressure. If we change pressure, what happens with wind speed, and so on. So we need to know the relationships between the variables to derive a model, okay? And once we have the model, we would try to make it more realistic. So we would fit some data to it. And that basically means we would take into account, for example, the variables that I told you about, but today, okay? So that is information that we have in hand. So we have the humidity today, we have the temperature, we have all of these things for today, yes? And that would be fitting the data. And then once we have all of the data, we put it in the equation and we solve the equation, okay? This is not always simple, but once you get a solution, it's very satisfying because that means that you can predict the weather tomorrow, okay? And then because you just have a solution in terms of maths, you need to, again, translate that back to the real world. So the equation itself is not telling you much. What is telling you a lot is the interpretation and the analysis that we make. So, for example, it might tell us that humidity goes from this number to this number, from today to tomorrow, but we need to say, oh, then it will rain, or this will happen. So the translation to the real world problem, again, is very important, especially when you're working with people that are interested in the outcome and maybe not so much in the inner workings of the model. So I've told you a very streamlined version of the process, but there are a few like gray arrows here that will tell you that it's not very straightforward, it's not very linear. So sometimes you derive the model, you try to fit the data, you figure out, oh, something is wrong, I missed a variable, the data is not the correct thing, and you have to go back, derive the model again. Sometimes you solve the equation, but the solution is doing something funny. So if I have more temperature, pressure decreases or something like that. And that should not be happening, for example. So then you have to go back, derive the model again. There was something that you missed. And sometimes you get right to the end, you translate it to the real world problem, and I predict that it's going to rain tomorrow. It doesn't rain. There was a problem with the model, yes? So we have to iterate again. Okay, so that is the overall process. So now who is part of the process is really important. So in the first instance, so when we're talking about getting the real world problem, it could be almost anyone that has a problem that can be quantified. Yes, so it could be government trying to figure out if they should do lockdowns now or in a month for a pandemic. It could be industry trying to figure out how misinformation is spread in social media. It could be charities trying to figure out where to target homeless people to do some intervention to get them in a home or something like that. So it could be all sorts of people that have a problem that you can count. So you can count people, you can count all of the things that I said before. So then once you have a real world problem, you would simplify it a little bit and translate it to math. And the people that are doing these things are usually the people that speak the language, that speak mathematics. And this would be mathematicians, engineers, scientists, and this could be social scientists, natural scientists, all sorts. And then the people that derive the model and feed the data needs to be either someone that can do both things at the same time, or it needs to happen in collaboration, okay? So you need people that understand the language, that understand the underlying phenomena, so that understand the real world problem that is happening, and how physics or biology or chemistry is involved, for example, and that can also gather the data. And this could be mathematicians, engineers, scientists, again, working together. And once you do that, you solve the equation. Most of the equations that we use for modeling are already known, the solutions, but in some cases it's unknown, and then that's when you call us mathematicians to help out. And then you have to go back, translate it to the real world problem again, and that is in collaboration between the people that made the model and the people that will receive it and apply it to something real. Okay, excellent. So now we're gonna do our own modeling, okay? Because the best way to learn is to do. Okay, so we're going to talk about exponential growth, and I have a very specific example here. So I hope you know about Escherichia coli. It's not a very nice bacteria, especially for humans. But this bacteria, we have pictures of it every 20 minutes. So we have a first picture here on the left, where we have one bacteria at time 0. So this is our initial condition. That's how we call it. And then in the next 20 minutes, we have 2 bacteria. And in the next 20 minutes after that, we have 4. And then at an hour of time, we have 8 and then 16. Okay, so you can see that it's doubling every 20 minutes. And I've made this table here that has the time, the population number, and at 0 is 1, 20 is 2, 44, 68, and 80, 60, okay? So now we want to express this mathematically. And the way to do that is through an exponential, okay? So the equation at the right top here is the mathematical model that describes this. And it's broadly saying that the rate of change of the population in time, that is, in other words, the speed at which the population is growing, is directly proportional to the population at that point in time. And in other words, it means that it grows like the graph that it's on the left. So if you can see here, at 0, it's very hard to discern, but later you will see. So at 0, it's 1, at 20 minutes, it's 2, at 40 again, and same. And then at some point here, between 120 minutes and 140 minutes, we have gone above 100, and then it starts to jump very fast. Okay, so this is what we call exponential growth. And the possible solutions from the model that I showed you, the equation at the top, are of the form of this, okay? So C and K are constants. K is the rate of growth of the bacteria, and T is time here, okay? And after fitting the data, that means finding C and K from the observations that we've made, you get something like this. And for any T, this will tell me exactly how many bacteria there will be. So this function exponential is due to Euler. I don't know if you've heard of him. He did many things in mathematics and physics. You can look him up. But yeah, so that is our first model, exponential. So now I want to ask you a question. Is this a good model? And how would we know if it's a good model? So can bacteria grow forever? Like if this keeps going on in time, the number of bacteria will explode, yes? So the issue is that in reality, bacteria numbers don't explode. Otherwise, we would be covered in it. We couldn't even breathe, okay? So what is going on here? So if we look at data in this graph on the left, what we have is the exponential that we had before in the blue dots, and then the data is in the red crosses. And can you see that the data is going in a different direction? So it looks like the model, the exponential model, is very good at the beginning, and then a little bit here until we reach around 380 minutes. And then it starts to deviate from the model, the data. So there's something that we're missing. And what we're missing is that, well, bacteria don't have infinite space to grow. They don't have an infinite amount of resources of food, yes? So what happens is that we need to add that somehow. We need to add this capacity for the environment to have this population and maintain it in time. And that's what we call a carrying capacity for the population. And this is what we will denote M. Okay, so M is telling us how many bacteria can the environment take. And you might imagine that this kind of number is very important, especially for if you're thinking of how many humans can Earth take. That's a very interesting question. And the model is this equation here. I might have time later to talk a bit more about this if you're interested, but basically we are just, this equation here is saying you behave exponential at the beginning, and then you go towards the carrying capacity. So in this case, the carrying capacity is around this 1 here, which is 1 to 10 to the 6, which is 1 million. So 1 million bacteria is the carrying capacity, and it would go that way. And it looks exactly like this. So here on the left, you can see the exponential, again in blue dots, the data in red crosses, and then the logistic model, which is the one that we were seeing before, in yellow line. And you can see that it fits much better, yes? And when the data is deviating from the exponential as time goes by, it goes to the carrying capacity. So how do we, I said the word, I use the words good model, but what does this mean? So good model is one that fits very well to the real data, yes? And we can quantify this by the use of an error. So error, broadly speaking, is the data minus the model, yes? So it will be telling us what is missing from the model to be closer to the actual data. And good models have small overall errors, okay? And that is very, very important. You always want to ask, when presented with a model, you always want to ask, okay, but what is the error? Is it actually close to reality? Okay, so I've shown you a bit of, well, not a bit, some few equations and a lot of maths. And now the question is, well, how does this affect us, really? And I kind of hinted at it before. So how does this shape our decisions? And the model that I've shown you, the logistic model, is a simple version of more complicated models, more probabilistic versions that are used today to calculate the population of the world and make predictions for example, 2030, 2050. So in 10, 20, 40 years' time, how many people will we have in the world? And why should that matter? Well, everything that we are planning to do is linked to that. So the amount of energy that we need to heat the homes of more people, the amount of food that we need to feed that population in 30 or 40 years' time, the amount of housing that we need to do, how large is our job market? Will we have enough jobs to satisfy the population and to keep them working? So these are all very heavy questions that are linked to the model. And if the model is not accurate, then we have a problem because we cannot make good decisions on bad models. But if the model is very accurate, then we can make very good decisions and predict what will happen with some very good accuracy and precision. So now we're going to move on from exponential growth to exponential spread. And I know you have seen pictures like this before. So this is a picture of exponential spread. So one person spreading something, for example, a virus. to 3 people, and then each of them spreads the same virus to 3 other people, and so on. And this grows exponentially. And yes, I did take the time to do all of the little people on the right-hand side. So it's correct. Okay, so let's talk about disease spread. And I didn't want to start with COVID because it's been overdone. We will talk about it later, but I want to go back to the bubonic plague. So this is also called the Black Death. And if you've seen this picture on the left, well, you know a little bit about it already. So between the years of, between the 1300s and 1600s and 1700s, there was a plague. And this was spread in fleas that mice took and contaminated humans. And then between humans, you could also have disease spread through air droplets, okay? That is the type of thing that we will be modeling. Now, the model looks like this, and don't despair, we will talk a little bit about it. So the main idea of the model is that the variables are the number of people that can get sick. So these are the people that we will call susceptible, S. The number of infected people, these are the number of people that are sick. The number of people that are removed from the system, so these are people that are either recovered or dead. And alpha is going to be our rate of recovery, so how fast people recover from the disease once they are infected. And beta, what is the rate of transmission? So how many people can one person transmit this disease to in a certain amount of time? So broadly speaking, this model is telling us that the rate of the speed at which people get sick, for example, is directly proportional to the people that are being infected minus the people that are getting recovered, okay? So that is the underlying law. And what are the underlying assumptions? Where actually this one has very few. The main one is that there is no migration, so the population is stable. There's no one going out of the system, there's no one coming in. So if you were a country, there would be no migration. And now, so if you want, you can go to that link over there. Maybe I'll put it in the chat. And I'm going to share again my other screen. So I'll put it in the chat later, but basically is an applet that allows you to play with this model. So this is the solution, and you can see the susceptible, removed, and infected curves. And the infected is the red one. And you can see the peak over there, okay? So if we take transmission to be lower than what we have, so if one person transmits less to less people, then the curve, the red one, goes down, yeah? There's still a peak, but it's lower, and it's also happening slower, okay? If the transmission is very high, then the peak is higher and it happens earlier. And now if the recovery is higher, so we get very good recovery, then the peak is also less, which makes sense, right? So you can play around with that when I put it in the chat. Okay, can I do that now? Let me wait a second. I'll do that later. So let me go back to the model because I want to show you what actually happened with the bubonic plague. So the model that I just showed you is called SIR. because of the names of the variable. It's not very creative. And it was made by these people here. Both of them were not mathematicians. They were in epidemiology and medicine. And this is the model for a small village in the UK, for which we have very good data, thanks to the reverend of the village. And the data are the crosses, and the model is the full lines. And you can see that it fits very well. It can predict the infection line and how people will unfortunately die, and the people that are susceptible to the sickness. And well, why do we care about this? I think this one is quite obvious why we care about this. One of the things is because we want to make good decisions in government about how to avoid pandemics, how to mitigate them. And we especially want people in government to know what the words that they are using mean. So for example, Professor Chris Whitty here basically said that officials shouldn't use the words flatten the curve if they don't know what they mean, if they don't know which curve they're talking about, because it's not the same thing saying that you want to flatten the infectious curve, so the red one that we saw before, or if you want to flatten, for example, the R curved, or so on. So it's not the same thing. And flattening out, it also means having it longer, for longer time in this state, okay? So it's very important that we actually know what we mean, particularly for people in power. And this one kind of made me laugh. I hope it, I mean, it's horrible, but also quite shocking. So Sir Patrick Vallance was talking about how some officials had problems with absorbing concepts central to COVID, like flattened infection rate curves, but also this was not localized to the UK. So many scientists were experiencing this issue with like leaders not understanding what an exponential curve is. And this matters because exponential growth is the fastest growth that can exist here in this case. So it's the difference between saying we need to do a lockdown now and saying we can wait a couple of weeks. And that difference can be measured in lives, which is why it's so important that we actually understand what's going on behind the scenes. So now I'm going to go. So another important thing about lockdowns and all of that is that all of these models allow us to decide on mitigation measures. So here is another figure that you would have seen in 2020 at some point. So this is critical care beds occupied per 100,000 of population. And these are under different measures. So do nothing, if there is isolation, and quarantine and so on. Other of the measures that we had to live with was social distancing. And that was especially strange, social distancing, and when we could go out and have exercise, because it was about all of us making a decision on how we use everything that is public space. And those types of decision can be modeled with another model called the tragedy of the commons. And this one is very widely used in economics and sometimes in politics. The original story starts with a pasture called a commons in the UK, and farmers trying to divide the pasture who can use it so that they can feed their sheep. So that was the original problem. And the main assumptions of this model are that everyone has access to the pasture, so there are no restrictions. The pasture will deplete in time, so it's not renewable, or not completely renewable at least. And one person's use means that another person cannot use the same space or pasture at that time. So here we have two farmers that are trying to decide, okay, so how do we divide the pasture? Okay, how do we decide on that? And turns out that we have some models that can help you do that. And one scenario is where you maximize your individual gains. So you maximize only, you're thinking only on the amount of sheep in your farm that you can feed with this common pasture. And if both farmers are thinking about that and trying to get the maximum amount of sheep and pasture that they can possibly use, then the model has this outcome. So that means that each farmer will use 1/3 of the resource today, so 1/3 of the pasture, and they will leave 1/3 for the future. And tomorrow, in the future, they will divide the rest in half and use, each of them will have had half. So the resource is completely depleted in this model, but it's also not used in a sustainable way because they use 1/3 at the beginning and then half of that. So how does this compare when we have some social conscience? So what if we maximize for social gain? So that means that instead of maximizing only instead of thinking only of my sheep getting fed, I'm thinking of both of our sheep. So how do I include other people's point of view? And in that version of the model, there is a more sustainable use of the resource. So today, the farmers use each 1/4, which is less than 1/3, which is what we had before. And then they leave half of the resource for tomorrow. And then they divide that again, half and half. So they end up, again, depleting the resource. All of these models work that way. So they deplete the whole of the resource, but in a more sustainable way. So now, there are some possible solutions to this issue of depleting the resource, and how do we move people from the individual gain mindset to the social gain so that we are more sustainable. And the possible solutions are in the literature and among economists and politicians are either private ownership, government or international regulation, so putting laws in place, community-based management. And all of three, I don't know if you can see it, but there is a clear undercurrent of politics behind this. So depending on your politics is what measures you will be inclined to take. So we went from a model to a political decision on the outcomes of the model. So unfortunately, the tragedy of the commons has been used again and again in the past to say that private ownership is the way to go, and not everyone agrees with that. And today, actually, the tragedy of the commons is being relooked at as more of a metaphor than a guiding principle, or maybe a misunderstood guiding principle that needs to be more complete. And part of that is the issue that people apply it to all sorts of resources, common resources. So for example, forest and deforestation, pollution in rivers, fishing in the high seas, and well, sheep, which is the version that we saw before. But does the model actually apply? Okay, and this speaks to the suitability of the model and if it's limited or not. So the assumptions for this specific model, the tragedy of the commons, is that everyone has access to the resource, but does everyone has the same access to polluting a river, for example? I don't think so. That the resource is depletable, in most cases that's true. That all parties want to maximize their individual gain, that's also not necessarily true. There might be individuals that are trying to maximize a social gain or some other type of gain, especially if it's a government or some representative of a population. Also, you need that all parties have common knowledge. And this broadly means that everyone knows the same facts about the situation. And this is clearly not true in many cases. Industry can have more information on the amount of pollution that they have and the pollution that they actually report. So the government might not have all of the information. this is not always true. And the final one, all parties have impact on the outcomes. And this is especially not true when we have things, for example, like river pollution in the UK, where a lot of the people affected are individuals that live near or have water that is, or bathe in the river. They don't have the same impact if they made a decision than a company or a farm or the government, yes? So these are all things that the model is not factoring in. And this is because, as Elinor Ostrom said, and she was the Nobel Prize winner in 2009 for economics, she studied these types of models and included some more factors that made them more accurate. And as she very well said, these are special models that utilize assumptions rather than general theories. For example, in the epidemics bit, we have some more general information. In physics, we also have some more general laws. And these models can predict strategies and outcomes in some very specific situations, but they cannot predict outcomes outside of that range. So if you had not thought of the right variables, then your model doesn't have the capacity to grow in those directions. So the person that does the model matters, and the assumptions that they do also matter. And that goes to these 3 points. So models can help us tell at least part of the future. They are not perfect descriptions of the world, but they are not meant to be, yes? They are meant to capture only the essential bits. But we decide what the essential bits are, basically. So the assumptions matter, and they tell us about how our model has to be used, how limited it is, or if it's very accurate, and we can get some information there. So as a summary, we have seen models that focus on essential features of a phenomena and allow us to predict how a variable will behave. This requires simplifying with assumptions. We can quantify the limitation through errors. We have 2 main types of models, data-driven, assumption-driven. And we've seen examples in population growth, disease spread, and common resource allocation. And if you want to know more, this is the book by Dr. Erica Thompson. I recommend you read this. It's very low on the mathematics, but it goes over, I don't think it has equations at all, but it transmits the message that I've been trying to tell you, that we just need to be critical about the things that we are absorbing, and we need to take care that when we are making a decision based on them, that we are sure. So this is a very good starting point. If you want maths, then I suggest Science by Simulation by Andrew French. This has many exciting topics with different levels of mathematics. And you can see the pandemics example here. And if you want to know more about the economics and the tragedy of the commons, Strategies and Games has, from Dutta and Fergote, has some maths, but it's a very nice introduction to the area of game theory. So thank you, everyone.
Great, thanks so much for that, Catalina. That was very interesting. I'm sure everyone agrees. If you have any questions, please do drop them in the chat or the Q&A. We do have a couple that we can ask you now.
Catalina, I've emailed you some ones that I want you to focus on. So if you go to your email, I've selected some that I think you should look at.
Okay, cool. So there's one here. So I understand that finance and stock exchange are seen and analyzed with econometric models. Oof, yes. So these are a mixture of the population models that we have seen today, but with noise. And noise means that we add some probability elements, something that it's random. And these are actually really hard to analyze. And there are people that spend their lives trying to solve this to, for example, predict how stock might change or things like that. And this is why people in finance are paid very well. And the next one, I would like to know what mathematical model can be used to study ocean freight rates along the time. Maritime transportation is responsible for 90% of all global trade. So mathematical models that can be used to study ocean freight trade. I think you could use, so most of these are already using some kind of mathematical model because they have to take into account how the ocean behaves. So all of the fluid mechanics that goes into that to have the best route, because they're usually minimizing the amount of oil and energy that they use. So they're already doing that. I would have to think about what other models we could apply there. But yes, so that is a big one that they use. So they use, they choose the routes based on the ones that minimize the amount of oil that they have to use. So the next one is, what error metrics have you used and seen used? So for example, root mean square error. Do you see different disciplines or sectors use different error metrics? Have you seen other ways to quantify the goodness of a model? So there is, oh my God, there are so many versions of errors that I've seen. And this is a very good question, but basically my broad answer is there is a lot more under the surface. And it depends if you are just doing statistics on your model, or if you are trying to account for other types of errors. For example, if you are solving a very hard equation, that means that you have to go through an iterative process, and you have to ensure that somehow that iterative process ends at some point. And yeah, you have another error there. There are tons of places here, but yeah, you can look up more errors. But root mean square error is one widely used, especially if you are just starting and you want to compare the data to the model. The next question was, which careers or degrees are focused on this? On mathematical modeling specifically, well, I touched upon this at the beginning, but very few careers focus particularly on this, because it kind of appears. But I would say anywhere that they teach you some physics or mathematics would have some of this. Applied mathematics mostly, because pure goes in other very different directions, but it goes into everything. Like, I've worked with people that are trying to figure out how electricity travels through neurons. And you have to work with people from biology and medicine to go through that. So yes, you will find a lot of people working on it, maybe not having learned that at the beginning of their higher education journey, but eventually having to pick up more of that. We do a lot of mathematical modeling at LIS. It's one of our core parts of quantitative methods. I mean, models is all that we do, because so there are the statistical models, which we spend a lot of time on, and there are the assumption-driven models that Anson and I work on and teach also here. And the last question, how does data bias impact the development of an accuracy, precision, for example, of mathematical models? So how does data bias impact the accuracy, precision of mathematical models? Well, I would say that is very hard to quantify, because we need to be very real with ourselves. If the data is, there is a phrase that people like to use, that if you put rubbish into the model, you will get a rubbish outcome. So you need to make sure that your data is as unbiased as possible. Sometimes this is not entirely possible. This is why we prefer to do mathematical models on things that have underlying laws, like physics, chemistry, biology, so on the natural sciences. And the models in the social sciences, some of those have very deep roots that are very well justified, and some of those, like the tragedy of the commons, it's not as well justified in data, or the data that was used was biased. So you need to be careful there. But yeah, I would say that it affects it. It's really hard to see how much, because we don't have people that are going like and picking and comparing models all of the time to see how biased they are. But yes, it definitely impacts them. So that is why you have to justify your model very well and use it, and use different sets of data to compare it to. Okay.
There are 3 more questions in the Q&A bit that we've left open. So if you go to the Zoom Q&A box.
Yes, so I see the 3 questions. Thank you. So thanks for the interesting speech, says Krishna. My question is, how does a mathematical model address the uncertainty involved in a complex system? Can you make a simple example? So uncertainty is a big problem, especially in complex systems, because we have something called chaos. And chaos is when our outcome can be unpredictable. And no matter how accurate we try to be in the real world, the model will be unpredictable. And there is a nice blog post by me in the LIS webpage if you want to learn more about that. But yes, so that is one way in which it is a problem. There are other ways to address uncertainty. There are models that explicitly put it in. So if you have a probabilistic model and you add some noise, you are purposely putting it there to make it more realistic. But that adds some uncertainty. So everything that you speak, the outcomes from the model will be in terms of probabilities, it will not be completely certain. And also data comes with confidence intervals and uncertainty itself. And next question by Israel, how do we measure social impact of specific actions by companies? For example, employment support through CV advice workshops. So how do we measure social impact? Oh, this is a really hard question, because we try to do this all of the time at LIS, because many of our students are interested in these exact questions. So we would try to quantify some aspects of the social impact. So how many people have changed their behavior because of it? And you would usually use statistics for this. So you would ask, is my hypothesis that this has had a statistically significant impact true? And you would try to test that out with statistics. But yeah, you would try to quantify it in some ways. For example, in the amount of people that have changed their behavior, how they have changed it, what time it took them to change it, and all of that. And the next one by Mercy, what is the most difficult part working with models for you? Well, solving them. Solving them is usually the hardest part, because I like models that are not simple, and that means that the solutions are hard to find. And the last one, I want to do a social impact answer, how I can do it with LIS, a social impact as well. Well, that is why we have problems models, especially the individual problems models at the end of year 1, year 2, and then the year-long capstone at the end. That is all about that. And actually, the capstone has a specific requirement that you have to have real impact outside of academia. So yeah, so you have space every year to do that. Thank you.